Yeah, so basically, the thing is that I think so in this particular course, I think there might be two TAs who might be teaching this course. So I do not know about the other TA, but I think they may have actually appointed two TAs for this course. And
Yes, sir. That is why today's attendance is very thin, sir.
sorry.
Sir, since we have 2 hour session yesterday on the week two, that is why the attendance is so thin today, sir.
Oh, I see. Okay, okay, okay. Fine, fine, fine. Possible. Yeah, possible. They might be feeling that what's new in this. So yeah. Anyway. But yeah, basically they have like you have the opportunity to attend like both sessions. So and you will get the recording of both as well. So the thing is that both will be I think independently covering problems on that, so I think you will have a good opportunity to solve a lot of problems and get your
Yes, sir.
doubts
Yes, sir.
cleared. So yeah, anyway, so you can make use of those opportunities as you might find them so you might find them useful, so the other DA might also give you some useful things. And yeah, so try to attend
Definitely, sir.
both of them like if possible. And yeah, so I actually will be covering the session every Friday from 7 to 9. The only thing is that because I was traveling in the last week, so I could not conduct it in the usual Friday 7 to 9 slot. So that's why I requested them to conduct it on this Tuesday slot today. So I think it's probably will happen like this. I think the one session will happen on Monday and the other will be on Friday. So
Yes,
yeah,
sir.
yeah. So fine. So that will I think that's how it will be. Does that answer your question?
Yes, sir. And that is why the attendance is so thin because other participant thinking that this is a repeat session, sir. I think this is the
Oh,
session which you couldn't take because of your travel, sir.
yeah, yeah, exactly. So that's why I could not conduct it on the Friday slot. So that's why. So the other is on other session is on Monday, is it? Like
Yes, sir. Monday, sir.
Monday, okay. Monday 6 to 8, right?
Yes, sir.
Monday 6 to 8. Okay, fine. Fine, anyway, so you can actually try to attend both of them. So it will be useful for you in any way. So we are both conducting the session independently and it's like totally different. So there might be some overlap, there may be some problem may be repeated here and there, but largely it is like independent and yeah, that way. Okay. So did you attend my last the session which was for the week one?
Yes, sir. I have attended, sir.
Okay, fine. What about Karthik? Karthik, right?
Yeah, sir. Those are 5%.
Sorry.
2% in my first session, sir, which I'm attending.
So this is the first time, right?
Yeah, yes, sir,
So
yes, sir.
can you just tell me about yourself? Like what is your background? Are you a student or are you a working professional or how is it?
So actually, I'm a working professional, sir. I have done my MTech in automotive engineering, and I'm working in an automotive industry only,
Okay.
with 15 years of experience.
Okay, great. Okay, great. Yeah, so that's great. So what's your motivation to join this course?
Sir, actually, to be frank, sir, I'm involved in 1 day simulation. So 1 day simulation of crank involved in lubrication and all.
Okay.
For the crank simulation, I feel this vibrations related to torsion vibration and all. We do the simulation part, go for the damper selection and all. I just want to revise all my BTech things what I have done at that time, so that I start using hand calculation also, apart from depending on the software though.
Okay, okay. That's interesting. Interesting. Good. Glad to know and welcome, Mr. Karthik. So I think you have a lot of industry experience with you. So
Yes,
may I
yes,
know
sir.
which company are you working in?
So I'm working Volvo Eicher, sir. Volvo Eicher.
Volvo
Volvo
Eicher.
Eicher.
Okay, and
Yes, sir.
and you are working from like from which location?
I'm working from Pithampur, sir. Pithampur, Madhya Pradesh.
Madhya Pradesh. Okay, okay. Yeah.
Yeah, yeah,
Yeah,
Pithampur. Yeah, we say it as Pithampur. Yeah.
sorry?
And I'm basically, it is Pithampur, sir. Location is Pithampur.
Pithampur. Okay, okay.
Pithampur. Yeah.
Yeah, yeah, I got it.
And I'm working on the engine simulation, sir.
Engine simulations. Okay, okay.
Yeah. Yeah.
Sure, sure.
And we
Glad.
normally we use the AVL software. AVL software is called Excite Power Unit. We work on that.
Okay, okay, okay. So you are like which software of AVL you mentioned?
So it is Excite Designer for 1D simulation. We also use Excite Power Unit for 3D simulation, for 3D parts.
Okay, okay, okay. Yeah, okay, interesting. Right. So I also happened to work in industry for a few years. So I was
Okay,
working with
okay,
Eaton for a few years. Like I worked for
okay,
about 2.5 years in Eaton in Pune. I was
okay,
also working on 1D simulations, but for powertrain, like vehicle powertrain modeling and simulation. So
okay, okay,
yeah, so I was mainly because Eaton manufactures gearboxes for commercial vehicles. So
okay,
I was basically working on uh, using like building vehicle system level powertrain models, or basically it's like name like it's similarly known as 1D like powertrain simulations, and
okay, okay,
using those models for different simulation studies, like estimating fuel economy or acceleration performance of vehicles with different powertrain
uh,
concepts, like different gearbox like gear shifting strategies, testing them, and
okay, okay,
then like different even gearbox concepts, like then evaluating and comparing them, like benchmarking different transmission concepts, and
okay, okay,
yeah, and then also like I was also working on like electric and hybrid powertrain simulations. So,
okay,
so I have also been working on in the automotive industry, and we also had
okay,
a
okay,
division where like we had like driveline dynamics, and where we like there are a
mm-hmm.
lot of vibrations and all these kind of things involved. So yeah, so it's good to know like this basic theory so that it helps in your like daily work. So yeah, so
And one more
glad.
thing, sir. Yeah, one more thing to add, sir. I feel for Eton, you would have been working in 1T cruise software over the cruise AVL cruise. That is for
I
vehicle SE and all. Yeah, we have a
Yeah.
software called cruise software.
Yeah, so I think there are some industries which use AVL Cruise, but we did not use AVL Cruise at that time. We were mainly using MATLAB Simulink and
Oh,
GT
MATLAB
Suite.
Simulator. Okay, great.
Yeah, MATLAB Simulink
GT
and
suit.
GT Suite.
Okay, 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 okay.
Yeah.
And apart from sir, and one more thing, just wanted to add on. Apart from this transmission components, I feel Econ is also into the watering side also. Because
Yes.
recently we have developed HLA for hydraulic gas adjuster from Econ only,
Right, right.
and uh, and they were also into this compression brake concept and all. Uh, so compression brake. Hope you would be aware of that compression
Yes,
brake of
yes.
engine.
Yes, yes, yes,
Yeah,
definitely.
compression
Yeah.
brake, meter brake. Yeah, meter brake, compression brake. Yeah.
Yes, yes, yes. So yeah, yeah, couple of colleagues of mine were also working on these valve train related products, and yeah, I remember like I have heard of these things like about the brakes and
Okay, okay,
yeah, right, right. So yes,
okay,
so
great,
yeah,
great,
Eaton
great,
also
sir.
was working on these things. They had these products
Yeah,
related to valve train also. Yeah, right.
yes, yes, sir, yes, sir. Okay, sir,
Yes.
okay, sure.
Sure. Yeah, glad to know, and yeah, welcome, sir. I hope you find these sessions useful, and do
Yes,
let
sir,
me
sure,
know.
sir, sure.
Yeah, so do let me know. So please do have a look at the recording of my first week's session. So let me know how you find that, and if you have any questions, so you can always like ask me during this live session, or you can also post your questions on the discussion forum for the course.
Yeah, definitely.
So either related to the course content or related to these live sessions. So If you have any questions, so you can post them, and I'll also try to answer them to the best of my knowledge. Uh, yeah,
Yeah, yeah, sure, sure, sure.
sure,
Sure, sir, sure. Thank you, sir. Sure,
sure.
sure.
Yeah, so
Thank
I
you.
think, yeah, so I was planning to give you a brief overview of the course content for this week. So if you already are familiar with that, so I think we can, just skip that. If so, just let me know, so whether you want me to discuss that, like what are the topics covered in this week. So do you want me to discuss that, or we can skip that?
Sir, you can actually go as per your agenda, sir, as per your preparation, what you have done for this session.
Okay. Yeah, what about, yeah, Amit? So yeah, okay, fine. So you say you may skip. Fine. Fine. Yeah, basically I had just prepared some slides on, like, what are the course contents. So but if, yeah, I think I can skip them. Sure. So in that case, so then we can just directly get started with the problem solving session. So so I did pick up some problems, and so which we can, go over and see how to solve them. But before that, like, I just wanted to know whether you have any questions from your side, that you have some doubts, any problems that you had.
Sir, I have a doubt from week one lecture, sir.
Okay.
Sir, this question is related to assignment one also.
Okay.
Suppose we have a cantilever beam with a span length of L meter.
Mm-hmm.
Okay, say this has been loaded at its free end.
Right.
Now it is very easy to calculate the natural frequency using the standard formula,
Mm-hmm.
because we know that static deflection can be found using a formula WLQ upon 3EI.
Right.
Now, sir, suppose that the same load is now shifted to the midpoint of the beam, sir.
Yeah.
So, will it change the frequency, the natural frequency of vibration of the beam, sir?
Yes, because like the deflection, basically what we model it as, like the entire, the beam is involved in the, the, uh, so how do we do that is basically we model the force, like, the force applied versus what is the deflection. So basically stiffness is force per unit deflection, right? So we
Yes, sir.
already know the deflection value in terms of the force applied at that tip. So that, as you said, like, WL cube by 3EI or whatever. And the force
Sir,
applied is also, let us say, W.
sir,
So
sorry to
the,
interrupt you.
yeah.
Yeah, my query is that when we are calculating the natural frequency of these beams under say some static load,
Mm-hmm.
will we always consider the static deflection of the free end or deflection of the point at which the load has been applied? Because now the point of load is different from its free end, sir. Earlier the load was acting at free end. Now
Yes,
load is
yes.
not acting at free end. Obviously the deflection will change. It will be higher than the previous one. So
Yeah.
my question is that when we calculate the natural frequency of the beam in such cases, will we always consider the deflection of the free end irrespective of load where it is acting, sir? Or should we take the deflection of the point where the load has been acted upon?
Yeah, so actually the thing is that, first of all, this approach of estimating the natural frequency by considering that, this WL cube by 3I approach, that itself is an approximation. See, because uh, the cantilever beam by itself is a continuous system. It is not a discrete system because it is a continuous mass. So,
Yes, sir.
whatever the flexural rigidity or whatever that they call, so 3 EI by L cube is, let us say, the stiffness of that beam. So but that is for corresponding to the load applied at the tip. Now the stiffness of the beam, with respect to that, let us say, now if you shift the load to the midpoint, now the deflection at the midpoint will be different. So the load applied, let us say, if we keep it the same, but shift it to the midpoint, then the deflection curve will change, and correspondingly its stiffness with respect to that point of application of that load will also change. So in a way it will change. So by that approach, if you calculate, like let us say, you will be easily be able to calculate, what is the deflected shape of the beam for the
Yes,
load
sir.
shifted to the
We can calculate.
midpoint.
Yes, sir.
Now you know the deflection value at the midpoint, and you also know the load applied at that point, so you will be able to estimate the stiffness. So so by root k by m approach, like root k by k, let us say k is the stiffness of that cantilever beam that you estimated using that method, and that divided by mass, so root k by m, that will be the like the natural frequency that you will estimate from that. But that is an approximation, in a sense that because the cantilever beam itself is a continuous system by itself, and it has its own natural frequency. So it's not actually the case that the natural frequency will change as per the the point of application of the load. There are The cantilever beam being a continuous system, it has infinite number of modes or infinite number of natural frequencies that it has. So the first mode, natural frequency, so if you basically, let us say, you can try this, like uh, you can take a steel scale and pull the end, like fix one end and pull the other end and release it, so it will oscillate something like this. So then uh, that is the first mode or first natural frequency that will be excited by that. So the vibrations will contain largely the first mode of oscillation or the first natural frequency. So have you studied waves or anything like that?
No, sir. Actually, I have gone through the book, The Strength of Materials,
Okay.
because in that book we have to calculate the deflection at points other than the free answer. So
Okay.
what I have done to solve this question, actually this question was given in the assignment one also.
Mm-hmm.
So the load was not acting at the free end as we generally discuss in our video lecture.
Yeah.
It has been acting at the midpoint, sir.
Right.
So, sir, so my query was that when we derive a formula for omega n,
Yeah.
okay, omega n is equal to under root k by m or under root g by delta static.
Right.
So that static deflection, which is because of this point load W,
Hmm.
should we take this static deflection at the point where the load was acting, or should we take the deflection always at the free end? Because
No.
the mechanical vibration book generally consider the cases of spring mass system which are when the force is acting at the free end, but this case the load is not acting at the free end, it is acting at the
Yes.
midpoint, sir. So that is why I have got confused, sir.
Right. Yeah, yeah. So your doubt is correct, but the thing is, so you can estimate it by the stiffness that you derived. So what I'm just told you, that you can derive the expression of the deflection at the point of application of the load
Yes,
divided
sir.
by the force applied at that point. So that will be the
Yes, sir.
estimate of the stiffness, because the
Okay, sir.
portion of the cantilever beam which is going to be extend beyond the, let us say, if you apply force on this, like are you able to see what I'm showing you? So
Yes, sir. Yes, sir.
now
Visible.
I have the pen in my hand, so then so I'll apply the like load over here. So now the cantilever beam will bend up to the point of application of the load, and beyond the point of application of the load, the cantilever beam will not go undergo any bending. It will have a the slope of the cantilever beam will keep to like will be the same beyond the point of application of the load,
Yes, sir. Yes, sir. There
right?
will be no bending moment, sir.
There will be because there is no bending moment acting on that. So because beyond the point of application of the load, there is no shear force acting beyond that point, right? So I think hopefully you are able to visualize, or I'll just quickly show you
Yes, sir. I
on.
got the idea. I remember BMD and SFD, sir.
Okay.
Sir, my query was that even there is no bending moment beyond the midpoint till the free end, but the deflection of the free end will be now greater than what will happening when the load was applied at the free end, sir? So will impact the value of omega, and sir, that is why my query, sir.
Uh, so can you just repeat what you just said?
Sir, I got your idea that there is no bending moment beyond the midpoint.
Right.
But but actually, what we are talking about is the deflection. Now,
Yeah.
even the load is acting at the midpoint, but free end will deflect more than the value which it has deflected earlier.
Yeah.
So my query is that when we are calculating the natural frequency in this case now, the
Mm-hmm.
second case,
Mm-hmm.
will it impact the value of natural frequency, because now we have shifted the load from free end to midpoint, but all the formula we generally discuss in mechanical vibration terminology, we consider only the free end, sir.
Yes, yes.
So
So
if I shift W to the midpoint, sir,
hmm.
obviously the deflection of the free end will change, and obviously the midpoint where now the load is acting is somewhat different now.
Yeah, so it will change definitely. It will change. So
So for calculating the natural frequency, which deflection should I take? The deflection occurring at the midpoint or deflection at the free end, which is acting now?
no, you should consider basically the deflection up to the at the point of application of the load,
Okay,
because
midpoint. That
that is
means
how it is actually derived.
okay, sir.
Because
Okay,
that why I told you that, because the cantilever beam which is hanging beyond the like beyond the
midpoint, sir.
whatever the point of
Midpoint.
application of the load, so there will be
Yes,
no
sir.
bending in that, right? So it will just follow the same, it will, its
Same
slope,
slope.
the
Yeah.
slope will be the same. There will be no further bending of that. So whatever deflection additionally that you will observe at the uh,
Free end.
free
Free
end,
end.
it is not the result of the completely as a result of the application of the force. So that is additionally because of its own additional length, right? So
Okay. Okay,
so
sir.
then you should only consider the deflection at the point of application of the load. Although
Okay. Okay, sir.
now whatever natural frequency that you will derive using that, the deflection at that point of the load, so
Yeah, that
that
will be different.
that deflection divided by the load itself, that will be the stiffness. No, so that will be the stiffness corresponding to that particular load and point combination.
Yes, sir. Yes, sir. Yes,
And
sir.
the natural frequency that you will estimate with that will be different than what you estimated for the load at the tip case.
Okay, sir. I got the idea, sir.
But this itself, just keep in mind that this approach by itself is approximate, because
Yes, sir. Yes, sir.
because uh, cantilever beam itself by is a continuous system. So there is a way to derive the natural frequencies. So this all these things do not come into picture, like where the load is or whatever. Cantilever beam has its own
Yes.
natural frequency, uh, and it there is a way to derive. So you will learn that. I think if you are interested in further, so I will direct you to uh, read like the book by S.S. Rao on mechanical vibrations. So
Yes, sir.
I do
I
not,
will go through that.
yeah, so I think you can go through that book, so you will find how it is derived. Or I maybe I in the next session, I think I can just briefly cover that. I do not have it right now because it's not part of the content of this week, but if you want, I can just briefly go over that in the next session. Just remind me. uh, so I'll also
Yes, sir.
prepare
Yes.
for, yeah, so I'll also prepare the slides for that, so that so we can briefly discuss on that as well. So there is a separate process for deriving the natural frequencies of a continuous system. So there right now we have ordinary differential equations. So the equation of motion that we derive. So we model like the system as a discrete one. So there is a block which has a certain mass. So then there is an element which has just there is another spring element which has only stiffness, and there is another damping element which has only damping. So there are like these three broad components. So you can always model a continuous system in this way. So essentially
Yes, sir.
when
I got
you,
the idea.
yeah, so when you when you are doing this, let us say cantilever beam with load at the tip, what essentially you are doing is you are modeling it as a spring mass system. So the entire mass of the cantilever beam you will lump it into one single block which has the mass same as the beam, and then the entire stiffness of the cantilever beam which you estimate with respect to the load deflection at that point, that you will replace it with a single spring. Now you have a single spring mass system and you can derive the natural frequency. Now that itself is an approximation. That's what I just told you.
Yes, sir.
Yeah, so
Thank
that
you,
is
sir.
an approximate way to model the cantilever beam. The exact way to model it is different because it is a continuous system. So you can always model a continuous system like approximately by this approach. Let us say if even if in in case of cars or like you generally consider models of this kind, like you entire like replace the entire thing by one single, that is called lumped parameter models, like these kind of things. So that's an approximate, or let us say if you're just trying to get an idea of the general behavior of a system, then you try to model it in this way. Like the first, like let us say the first approach would be like this way. So you can always go to more complicated models depending on what you need. So I hope you get the idea.
Yes, sir. Definitely, sir.
Yeah, fine. So then I think we can get, shall we, are there any further questions?
No from my side, sir.
Okay. So Mr. Karthik, so you have any questions or any comments?
No, sir, no. Right now, I don't have to. But
Okay.
next time I'll start with some of my practical experiments, which I will discuss in the session too, so that it becomes more exposure to you, and it also becomes a query resolution for me also. Please.
Yeah, sure. Sure.
Okay.
Okay, then I think then we can maybe start with the problems as such. So I'll just share my screen. So are you able to see my screen?
Yes, sir.
Okay. Yeah. Yeah. So I am basically using a tool called Google Jamboard, so which by which I can basically draw things and like use it like a blackboard or whiteboard or whatever. So yeah, so I have basically listed down some questions, so we can try to solve them together. So the first question is, so the torsional stiffness of a shaft having a length L, which is subjected to the torque T and angular displacement theta, let us say some theta. So let us say the angular displacement is theta and torque is tau. So let us say T. So how do we basically define the stiffness? So what is the torsional stiffness? How is it defined? Yeah, so it is basically T by theta itself. So, so what is the generally the expression for this torsional stiffness?
Sir, like we have spring stiffness K is equal to F upon X. In the same line, we can define for the shaft also. Force will be replaced by torque
Yes,
and displacement will be replaced by the angular value.
correct, correct. Yeah, so further, like, do you know what is the expression for the so depending on the material of the shaft and the geometry, how do you how do you define like evaluate what is like given a certain shaft which has a certain length and diameter, how do you estimate its torsional stiffness? What is the expression for that? You
Sir,
are right. So torque by theta. Yes, sorry.
it is G into J upon L, sir.
Right. So it is G into J by L. So where so what is G?
Sir, shear modulus of elasticity.
Yeah. And what is J?
Sir, polar moment of inertia of the circular section.
Correct, correct. Right, exactly. So it depends on the rigidity of the modulus of rigidity or shear modulus of the material and the polar moment of inertia and the length. So yeah, you're right. So yeah, so we'll be discussing like starting with some basic questions and then we'll move on to more complicated problems. So yeah, so there is a certain equation of motion given here. So 4x double dot plus 64x is 0. So then what is the natural frequency of the system? So 4x double dot plus 64x is equal to 0. So what is the natural frequency of this system? Four radian per second. Okay, right. So basically we can compare it with the form of equation like so then omega n square will be 16. So that is why omega n will be 4. So you're right. So yeah, so then we come to the next question. In Coulomb damping, the amplitude of the motion is reduced in each cycle by how much? So there will be like so answering this question needs some I think some understanding of how Coulomb damping actually behaves. So you may actually be directly able to get the answer if you memorize this thing, but I would recommend that, like, let's try to get some better understanding of, how this actually comes out. So maybe I'll give you 2 minutes to think about what this can, this, how to solve this problem. So let's just take 2 minutes to think about how to solve this problem. Okay. Yeah, so any idea about how to solve this problem? How do we start with, like, so if we want to solve this problem, like, from scratch, so what, any idea how to solve it?
Sir, we can use the energy balance equation. That means the energy, the change in energy in the spring is equal to the work done on the mass, sir.
Yeah, right. Yeah, that is also one way, correct. So how would you do that?
Sir, we can compare the change in energy in the spring, the half kx square, using the formula half kx square
Mm-hmm.
between the two peak points.
Right.
So that difference of energy will be equal to the work done on the mass, sir.
Correct.
So,
Agreed.
uh, yeah.
Agreed. So yeah, right. So can you elaborate, like, be more specific? So you are on the right track. So that is one approach to derive that. Agreed. So like, for you said that, like, you will compare, like, the peak difference between the peak points, but you don't know upfront where are those peak points, right? Like, you start with some point, the mass will reach between, like, oscillate between two extreme points. Like, let us say if there was no friction, then the two maximum endpoints will remain the same, so it will always keep oscillating between the two extreme ends, right?
Yes, sir.
Yeah, so in this case, because of friction, the mass will keep on losing energy as it travels. Let us say if you stretch the spring by a certain amount and then release it. Now, now can you just tell me, like, let us say if we now start with this, let us say, initial condition. So you can actually consider the system from different initial conditions, but let us say for now we start with this point. Let us say you stretch the spring by a certain amount and then release it. Uh, Let us say x naught. You start with a certain initial deflection x naught, let us say. Uh, then from the free length, let us say, then uh, what how will you find out then what is the other extreme point that it will reach?
Sir, the distance traveled by
Yeah,
the mass m,
right.
uh, that will be uh, change in the energy of the mass, and that we can equate with the change in energy of the spring, because spring energy is acting against the friction force, sir.
Yes, yeah, that is true. That is true. So, yeah, that is true that so like let us say there is when I stretch the spring, so there will be some initial potential energy that will be stored in the spring. Now, when we release it, there will be like so the spring will reach a certain point and it will acquire some velocity. So that will be converted into kinetic energy. And now the spring so when we consider a usual, let us say, frictionless case. So like let us say I'll draw, let us say, three positions of the mass. So let us say this is the equilibrium position, the center one. So this is, let us say, x naught. Now if this thing is frictionless, so then it will again travel the same distance x naught on the other side. So basically the entire potential energy of the spring will get converted into kinetic energy at this point, and then further this kinetic energy of the spring, so the kinetic energy of the mass will now get converted into the potential energy of the spring at this point. So uh, now in this case, so when it travels, so when there is friction acting, so there is basically conversion, like there are uh, so the first so when you release it from like the extreme end, then till it reaches the equilibrium position, there will be conversion from potential energy to kinetic energy, and this will not be conservative. So it will be, there will be some dissipation of energy, and because continuously friction, there is energy loss due to friction. So that will be basically the friction force into the distance traveled. So that will be, let us say, x naught amount of distance traveled, and so that will be the uh, so the half k x naught square will be, let us say, the initial potential energy of the spring, right? So now that will be basically equal to the work done by the friction force, which will be basically friction force. Now it is already sliding because it's already moving, so then the friction force will be equal to mu into normal reaction, so which is basically mu into, let us say, mg here in this case, because the mass is resting on a flat surface, etc. So plus the kinetic energy, which is, let us say, half m some v naught square. And now with this kinetic energy,
So there will be multiplication of x0 with mg.
yeah, correct, exactly, yeah. Fine. So this will be the the expression now for, let us say, if you want to derive the expression for the, let us say, the velocity that it acquires at the equilibrium position. So you can find out from that. And then let us say instead of x naught, it reaches some distance x1, something, a position x1. So the spring is, let us say, compressed by x1 now instead of x naught. So x1 is actually less than, so mod of x1 is actually less than x naught, because x1 will be actually negative. If you talk in terms of the coordinate, it will be negative because it is like towards the left hand side of the equilibrium position, if we consider the coordinate system in such a way that which is centered at the equilibrium position of the mass. So now the spring is being compressed by x1 amount. So now the energy stored in the spring will be half k x1 square, right? So that will be the potential energy stored in the spring. And now, so that will be basically, so how will we write it now in terms of the kinetic energy of the mass and the work done due to friction?
Sir, x1 into mu into mg.
Right. X1 into mu mg is the work done from the the
Main,
equilibrium.
main, yeah,
Yeah,
at mean position.
so let us say x1 is the distance traveled by the mass. So then it will start with an initial kinetic energy half m v naught whatever square, and it will lose this much amount of x1. Now we can solve for x1 in this way, right? Do you follow?
Yes, sir.
Yeah. So now what is half m v naught square? It is half k x naught square minus x naught mu mg, right? If you refer to the earlier equation, it is half k x naught square is equal to half m v naught square, sorry, sorry, uh, plus x naught, right? So basically we can substitute for this thing. So we can basically solve for x1 using this approach, and similarly, like you can, now like you start with the position x1, let us say x1, and then now the mass will come to rest at this position. So like you started basically with this position x naught, then you reach this distance x1. Now it will again come back from this to this position and then reach another distance x2, let us say. So what we need to find out is actually x2, right, after completing one complete cycle, correct? So what we are basically looking at is x naught minus x2. That will be the reduction in the amplitude over a complete cycle. So are you able to follow?
Yes, sir.
Yeah. So then we can get similar kind of equation like half k x1 square will be again half m. Now let us say we call it as half m v1 square plus additional work done mu mg x, sorry, mu mg x1, and then so v1 square is again the velocity at its equilibrium position, and from the equilibrium position onwards up to again the other extreme end. So then that will be, so half k x2 square now is equal to, so is that correct? So is that correct to write this equation in this way? So half mv1 square is the initial kinetic energy at the equilibrium position. Half k x2 square is the energy that the spring will have at the other extreme end when it reaches that x2 level, and minus mu mg x2 is the further distance that it has traveled from the equilibrium position. And so the further work done by friction will be basically uh, that one basically. So do you follow? So Amit, did you follow what I was saying?
Yes, sir. Yes, sir.
Yeah. Now so we have basically these four equations. So now if we now this half mv naught square is the thing that we can just, so we can subtract, uh, let us say let us say we call this number them equation 1, 2, this is let us say 3, and this is let us say 4. Now if we do 1 minus 2 and 3 minus, so then we will get further equations like so we'll get these two equations now. Now using the formula like a square minus b square is equal to a minus b into a plus b, right? Sorry. So therefore then we can use this. So x naught square minus x1 square is basically x naught minus x1 into x naught plus x1. And on the right hand side we have x naught plus x1. So it will basically get cancelled now. And we will be left with half k x naught minus x1, right? So k by 2 into x naught plus x1 is basically equal to mu mg, or if we take it to the other side, so it will be basically 2 mu mg by k, and now x1 plus x2 will be 2 mu mg by k.
So will there be minus sign between x0 and x1?
Sorry.
Sorry, please see the equation number 3, x0 plus
Right.
x1, sir.
Right. Correct. It will be x0 minus x1 and here x1 plus x2, right? Sorry, x1 minus x2, sorry.
Yes, sir.
Right. So then now what we have to do is add these two equations, right? So what we want is x naught minus x2, right? Because that is the reduction in the amplitude, correct? So that will be basically, if we add these two equations now, it will be basically x naught minus x1 plus x1. So x1 will get cancelled minus x2. So it will be we will be left with x naught minus x2, right? So we'll number this equation, sorry, as 5 and 6. So we have to basically add 5 and 6. So adding equations 5 and 6, what we get is x naught minus x1 plus x1 plus x2. Oh, sorry, I'm sorry, minus x2 is equal to 4 mu mg by k. So x naught minus x2 will be 4 mu mg by k. So that is our answer basically. X naught minus x2 will be 4 mu mg by k or 4 mu n by k, whatever. So, so do you understand? Like, did you follow what we did?
Yes, sir.
Okay. Yeah. Another. So, can you think of any other way to solve this same problem? How can we do that? This is one way. That you are right. So this is one way to solve it using energy method. So this was the energy way to solve that.
Sir, I guess using the partial differential equation for Coulomb damping, sir,
Partial differential equation.
by writing the standard equation mx double dot plus
Ah,
kx plus minus f is equal to 0, and then solving this equation and then finding the value of x at different points.
yeah. So that is not a partial differential equation. That's still an ordinary differential equation. But yeah, you're right. So that is how we can solve that. So we can just start with the basic equation of motion, then consider
Yes,
different
sir.
initial conditions, and then try to find the displacement at the different key points. So you are right. So basically, that's how we can do that. So we can like say that, write the equation as, so we can write it as like plus or minus mu n depending on the direction, because the friction force will change directions depending on the direction of the velocity. Now, so if we assume that, like, the mass is, we stress the spring, and then it starts traveling this way. So let us say the initial velocity is this way, then friction force will be in this direction, so till it reaches the other extreme end. And now when it starts uh, traveling back to the this in this direction, so then it will have the velocity like this. So in that case, the friction force direction will be this way, like the opposite. So now, depending on the direction of the friction force, we will basically change the equation of motion and appropriately solve it between the respective time intervals. So basically, this is, if this is t equal to 0 and this is, let us say, t equal to t1. So from that point, then the equation of motion will be something like this: mx double dot plus kx is equal to minus mu n, because friction force is, sorry, plus mu n, because the friction force is uh, acting towards the right hand side. And if we assume the sign convention like that, like right hand side is positive, then and for the, so this is for t equal to 0 to t1, and let us say t2 is the time instant at which it reaches back the, like it completes the full cycle. So then the equation of motion will change to mx double dot plus kx is equal to minus mu n, because the friction force will now change direction to left hand side. So then that will be basically t equal to t1 to t2, let us say some time t2, so where t2, so where t2 will be basically the time period, or basically, so 2 pi upon omega n, so where omega n is basically root k by m. So we can solve these equations of motion separately, and then find out what is the displacement at using the equation of motion at that particular time. So we can also solve it in this way, so you will get the same answer with that as well. So any questions?
Sir, I have one query regarding this Coulomb damping.
Mm-hmm.
Sir, can we model a spring mass system when there is only dry friction acting on it, like we have done in case of external harmonic force acting on a system, sir? Can we assume this friction force as an external force, sir?
Yeah, exactly, that's what exactly
Constant external force, sir.
yeah, that's what exactly I, I have written it in that form itself, like the way
Yeah.
we learn about forced vibrations, in the
Yes,
same
sir.
way we can
Yes, sir. Like a force vibration, sir.
yeah, so it's
Without
like a,
damping.
yeah, so it's like a forced vibration without damping, but this friction force will play the role of damping indirectly through this way, like it will change direction and it will constantly act with a, like it has constant magnitude, but the direction will change depending on the velocity. So in every cycle it will change the amplitude by 4 mu mg by k, that amount. So it's difficult to write one single expression for, what is the displacement for that, but so you have to solve it piecewise, because this force is discontinuous, because it's suddenly changing direction when you change the direction of the velocity. So
Yes, sir. It's like a rectangular force, sir.
yeah, exactly, it's like a step change, suddenly it will
Step.
change.
Yeah.
Yeah, so depending on the velocity, so if the velocity is positive, so it will be, let us say, uh, minus mu m, and then when the velocity is negative it will be plus mu n or something like that. So it's basically, so it's actually, mathematically you can write this friction force as uh, so the friction force is basically mu n into sine of, sorry, sine of x dot. So sine of x dot is basically, it's like whether when x dot is positive it will be, the value of sine of x dot will be 1, and when it is negative it will be minus 1. So like you can mathematically write it in that way. Yeah. So if there are any further questions, like, are there any questions further?
Yes, sir. Please proceed, sir.
Yeah. Okay, fine. So then Yeah, so then let's move on to the next question. So, as compared to the natural frequency of a simple pendulum on Earth, its natural frequency will be what? So, we are already like we know that acceleration due to gravity on the moon is 1/6 of that on the Earth, right? So basically G for Earth is so gra so GE is basically the gravitational acceleration due to gravity on Earth. So for moon it is 1/6 of that. So what is the expression for the natural frequency of a simple pendulum?
So root L upon G.
Yeah, so it's actually omega n square is G by L. So omega n is root G by L. So omega n on moon and omega n for Earth. So the ratio will be root of Gm by Ge. So right, so which is 1/6. So what is the value of this factor? Root 1 by root 6.
Sir, 0.4.
Yeah, so it's 0.4082. Right. So so that becomes 0.4082 times that of the Earth. So it is basically, so in terms of percentage, it will be basically reduced to 40.82%. So that's what it is actually. So so the natural frequency will be reduced to 48%. Got it?
Yes, sir.
Yeah. So this yeah, so let's start with a new question. So this is a question which actually appeared in GATE 2020 mechanical engineering paper. So are you aware of the GATE exam?
Yes, sir.
Okay. So are you planning to prepare for it by any chance?
Sir, I have already completed MTech, sir.
Oh, I'm sorry. Okay, fine. So you have completed MTech. Okay. So yeah, so you must have appeared for GATE and also you must be familiar with what is GATE exactly. So yeah. Mm. So yeah. So this basically this problem is about so there is a mass m1 which is moving with a velocity v naught and it strikes another mass m2 and so it travels along this surface is frictionless, it is given, and then it uh, like both the masses stick together and they jointly move by a distance of 0.25 meter further along the same surface and they touch the massless buffer that is connected to the rigid vertical walls by means of a linear spring. The spring constant is given. So now, so the masses will basically collide and then stick to each other. So they will acquire a new velocity, and then with that kinetic energy, they will basically cause a compression of the spring. So how do you think we'll solve this problem? So any idea how we solve this problem?
Using Newton's equation of motion, sir, we will calculate the velocity with which m1 strike m2.
Yeah, okay,
Then both will acquire the same velocity.
right,
With this velocity, they will strike this spring and give up their kinetic energy to this spring, sir.
correct,
That we will equate using the formula half kx square and solve for x.
right, exactly. So first, so there are two steps as you said rightly. So first step is basically to find out the velocity after both of the masses collide, so that we can use the the conservation of momentum principle. So basically, we assume that there is no external force acting along the direction of the momentum because the surface is frictionless, and along the direction of the velocity there is no external force acting at the time of the collision. So then therefore the momentum will be conserved. So the total momentum of both the masses combined together, we will equate it to the total initial momentum just before collision. So m1 into v naught, and because mass m2 is stationary, so it will be basically m2 into 0. So the velocity momentum of the second mass m2 is 0. So then we need not even write about that. So that will be equal to the combined momentum of both the masses. So m1 plus m2 into, let us say, v1. So therefore v1 will be m1 v naught upon m1 plus m2. So that will be the new combined velocity that they will acquire. And then we will basically have the kinetic energy of the masses. So half m1, sorry, so yeah, essentially we have to just solve for this thing. So from that we can solve for x. So it will be basically root of, so you can substitute the values of the masses and the initial velocity and then solve for that. So k is 10 to the power 5, m1 is 10 and m2 is 40, 30. So v naught is 2. So what is the value of x that you get? 11.18 mm. Okay. So okay, I am getting, just a minute. So I am getting it as 10 mm. So I think with, so just check your calculation. So it's just a calculation, whatever it is. So I got it as 10 mm. So so that's all, like uh, for this problem. So any questions on this? So shall we move to the
Sir,
next problem? Yeah.
this 1 meter data is, I think, no use for this problem, sir.
Yeah, it's of no use. Yes. So the distance actually does not make a difference because there is no friction. So if there was friction, then it does matter. Yeah.
Yes.
Yeah. Yeah. So this is the system shown over here. So Amit, are you also working somewhere or like are you studying some like?
Sir, I am working as a faculty member, sir.
So I think, yeah, you mentioned last time.
Yes, sir.
Forgot, yeah. Yeah. All right. So are you also teaching vibrations in your
No,
institute?
sir. Sir, actually, every time the subject allotted changes, sir.
Okay.
So, but the main purpose of going through this course is that I want to get refreshment because for many years I have not gone through these subjects, sir, in the classroom, sir.
Okay.
So, in every semester, I take one or two NPTEL course, sir.
Okay. 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 Good to know. Yeah. Sure. Right. So let's try to solve this problem. So this appeared in GATE 2021. So here we are given that like there is a rope that goes over a pulley. There is a mass M which is hanging over that rope. So there is this spring of stiffness K attached to one end of the rope, and there is no slipping between the pulley and the rope. So the pulley has a radius r and it has a mass moment of inertia j. So we have to find out what is the natural frequency of this system. So maybe we can. So I'll give you maybe uh, 2 minutes to think about this, and then we'll discuss. So any idea how to solve this problem?
Sir, we will displace the mass m by a small amount, say x.
Okay. Okay.
So,
Right. Okay.
and then we will write the standard equation as we wrote for a spring mass system, sir. But there is an extra component here, pulley.
Correct.
So that part will be added to that equation, sir.
Yeah. So how will that come into picture then? In that case, like how will you incorporate that? So
Sir,
Mr.
the
Yeah, Yogesh Poddar has also joined. So yeah, welcome, Mr. Yogesh. So yeah, so this session is actually 7 to 9 p.m. So we are almost like towards the end. But yeah, so if you like just for your information, so my name is Parth Joshi. So I am conducting these sessions every week. So I am a PhD student from IIT Bombay, and I am basically conducting these sessions every week. So generally I conduct it from Friday 7 to 9 in the evening, that slot. But since the last week I was not available during the Friday slot, so I shifted this session to Tuesday. But it will happen usually on Friday 7 to 9. So yeah. So we were discussing some problems on related to the course content for this week. So yeah, so we were just discussing. So let us know if you can contribute. So yeah, so Mr. Amit, you were saying something. Yeah, sorry I interrupted you.
Sir, one approach is that we can find the moment of the forces
Right,
about the center of the pulley. This is a standard approach generally we follow in these types of problems, sir.
right.
Like this mass is acting as a force
Mm-hmm.
mx double dot. So it is generating a moment about the center of pulley
Mm-hmm.
mx double dot into r. Similarly, this spring force, we can take the moment of this spring force about the same center.
Mm-hmm.
Similarly, in case of this pulley, which is the extra component here, so this can be modeled as j into theta double dot,
Right.
and sum of the all the moment will be zero if the system is under equilibrium.
Yeah, so it's actually, yeah, broadly, I think you are correct. Uh, so, yes, first of all, the system is not in equilibrium, so it will be oscillating. So, that sum of moment may not be zero. So, because the pulley has some certain mass, so it will again be accelerating, so it will not be in equilibrium. Now, what will happen because of the pulley is that because of the acceleration of that, because it is not massless, the tension on the two sides of the pulley will become different. So if the pulley was massless, the tension in on both sides, like on the spring side and the lower, like the mass side, would have been actually equal. But now because the uh, pulley has certain mass, so if we draw the free body diagram of the pulley, let us say, so then there it will have like two tensions. So the rope will, there will be two tensions. So let us say T1 on the spring side and T2, let us say, on the mass side. So the spring tension T1 is equal to the spring force itself. So let us say K x. So if we displace it by x amount, and because the rope is inextensible, it is given, then therefore the spring will also be stretched by x. So therefore the tension T1 will be same as Kx. Now the tension T2, for that we need to draw the free body diagram of the mass small m. So, so the tension T2 will be acting on this mass small m also. So now for that we need to write to what is to find out what is the value of the tension T2. We need to write down the equation of motion of the second mass. So so now we'll assume that this x distance, whatever it moves, is from the equilibrium position of the mass. So that's why then there will be, so the, so we can uh, get rid of the mg from the equation of motion. even if we don't, if even if we keep it, we will still have to basically subtract or incorporate the static deflection. So the static deflection will be, so the kx static will be same as mg. So we have to, so if x is the absolute displacement or so, so we'll have to basically subtract the static deflection from that to get the displacement from the equilibrium position. And then in that case mg will be included in the equation of motion. But let us say if x is, we assume it from the equilibrium position, then we, that will actually just get subtracted because of the static deflection. So because kx delta static is same as mg, so then it will, so we can just get rid of the mg term. So basically T2 will be, so mx double dot T1 is already kx. So for the pulley, as you said, we'll write the moment equation for the pulley. So the net moment acting about the center of mass will be T1 into the radius minus T2 into the radius, because T1 is causing an anti-clockwise movement and T2 is causing the clockwise movement. So that will be basically J theta double dot. Right. So now how this theta double dot, so theta double dot and x double dot, so they like, are they related?
Yes, sir.
So how are they related?
Sir, for small angular displacement of a pulley, we can write that x is equal to r theta.
Yeah, right, that is correct. So yeah, it's not only for small angular displacement, it is mainly because of rolling without slipping. So whenever the rope is, the cylinder is rolling without slipping, the distance that it is traveling, so if a cylinder is rolling on a floor and rotating by theta without, and it is rolling without slipping, so the distance that its center of mass will travel, so the translation is same as r theta. So in this case, the cylinder is stationary, but rope is moving up and down. So there it's basically when the cylinder turns by theta angle, so the rope is going down the r theta. So, so in that way they will be related. So so theta double dot will be same as x double dot by r, or theta is equal to look, x is equal to r theta in simply. So so either we can write the equation of motion in terms of x double dot or theta double dot or whatever. But so let us say, so we'll substitute now the value of this t1 t2 etc. So kx, So now, because now there is a slight sign convention issue in this. So when the x is positive, so or like basically if we are moving it downwards, so then the cylinder is turning clockwise, and if we are like moving upwards, then the cylinder will turn anti-clockwise. So we just also need to take care of that. So but yeah, so kx is equal to, so that's like the equation of motion. So and the natural frequency will be basically root of k upon this m plus j by r square. Yeah, here actually T1 should be minus kx. It's actually minus, so because the force is on the left, so towards the left. So yeah, so that's how like we can solve this problem. So like that's all that I had from my side. So any other questions? So there are also some more problems which I have actually listed down, but like I think we are almost out of time. So any other questions from your side? So maybe we can also discuss this one more problem. So I think this is simple.
Sir, can you share these problems? We can solve later on, sir.
Yeah, so that is also possible. So I can share these problems. So yeah, in this was also like asked in GATE 2023. So likewise, I also another problem which was asked in previous like GATE exam. So yeah, you can also try to solve these problems on your own. So yeah, so I'll share the list of problems also. So I have also one more problem sheet which I had prepared. So but yeah, I think we are almost out of time. So you can try those later on and let me know next time. So generally, how do you find the session so far? Like first one and second one, like both, like if you like if you have any feedback. So if it is too slow or too fast or whatever, like just let me know.
It's quite useful because just going through the video lecture doesn't give me confidence, sir. But when we start attending this session and solving the problem,
Okay,
that I think I get clear picture about the topic, sir.
okay, okay, sure. So shall we just continue with the same way that we are going, or any other suggestions that you want? Like if you are expecting something else, also let me know that like what. So like, is there anything additional that we need to do or discuss?
Sir, as a faculty, I think we should little bit more focus on the conceptual thing that why this is happening, not just
Right.
that this should happen this way only, sir. That will help us to learn the subject in a better way, sir, because this theory and question we can find in any book, any
Right,
previous year examination, sir. So I think little bit concentration should be on, like, we are going through the this topic, sir. We should learn how to model a given system into a spring damper system, sir.
correct,
I think that is a practical approach, sir.
right. So, like any particular like thing that you wanted to that you think that was like we need to understand like in the problems that we have covered so far. Do you think like I also need to add some more explanation in terms of why what is happening and like anything like that? So,
Yes, sir, question solving approach is okay, sir. That is no problem, sir. But sir, I think from my side, what I expect that our focus should be a little bit towards how we can model a given real problem into a these types of mathematical models, sir.
right, right. Fine. So then we can actually do one thing. Like we can actually
At least half an
consider.
at least sir, my request is that at least half an hour we should devote that how actually we can solve the real time problems, sir. Like one people is from industry, I am from also from teaching, sir.
Correct, correct.
So, so
Right,
at least we can say 10 to 20% time we can devote to just learning conceptually that how real time problems can be taken on the paper and solved in the research laboratories.
right, right. Sure, sure. So what we can do is, uh, you know, these are like very closed-ended problems what we are like discussing right now. So there is like a specific, like you know, specific, very specific question, and like there is like it has a one specific answer because you know like that. So yeah, so real life problems will not like you don't even know you're right. So in any real life problem that we encounter in industry or anything like that, so for that we do not have like just answer at the end of the book. So yeah, so then we'll have to model the system in certain way and something like that. So yeah, maybe I think we'll try to cover those kind of things also.
Yes, sir. At least we
Yeah,
can take one or two small problem, not very complex problem as you do in your research labs.
yeah, yeah,
Only part
exactly.
of that,
So
sir. Only part of that which is the level up to this course for which it has been designed, sir. 80% we can do the same approach, sir. There is no problem, sir. But 15 to 20% we can take small one or two problem which actually resembles with a real time problem, and we can discuss
yeah,
how we
okay,
can model it.
sure, sure. Another thing that we can also you know look at is how we can do some simple experiments. Since you are already a faculty member, I think what I can suggest you is like we can also try to see what how we can do some simple experiments in vibrations using simple uh, you know home like you know basic materials or basic things. Like if you are interested, like we can also discuss on that, like you know how we can
Yes, sir.
create
Sure, sir.
some simple experiments like that kind of thing. Like yeah, okay. Yeah, I'll also try to think on that side. So yeah, I'll make a note of these things. Thanks for your feedback and thanks for joining the session. So hope it was
Okay.
useful
Thank
for
you, sir.
you. Yeah, sure. Yeah, I think then we can end today's session over here, and I'll share the problem sheets with you, and then yeah, you can try them and let me know if you are able to solve them, and yeah, and if you have any questions you can let me know. So yeah, thanks for joining. So then there is another sheet, so which I also had prepared similarly, which had like you know questions from gate exam. So yeah, so these kind of problems I had. So yeah, you can try these and just let me know whether you are able to solve them. And yeah,
Yes, sir.
if
I will
required,
find from previous year's questions. These question I can find from the previous year gate examinations.
yeah, sure, sure. Like I have already done that exercise for you, so you can also try it right away. Like you know these questions. Also, you can like find out on your own also. Like no problem. So yeah.
And sir, there is a one more request. Can I know who is handling the discussion forum, sir? That our
I yeah, I do not know the person exactly. Yeah, what was the issue? Like any particular issue there?
Because many times, sir, we face some problem either solving the assignment or there is some problem in learning the concept, sir. So we
Mm-hmm.
put our query on the discussion forum, but
Mm-hmm.
the response is not encouraging. Either they do not reply or reply too late, sir. Because every
Okay.
assignment has a deadline. Like first and second assignment, the deadline is tomorrow, sir. So
Okay.
so some queries are to be answered at right time, sir, because otherwise we will miss the deadline, sir. So I request
Okay.
through you, sir, if you can convey our message that the question or query raised by the participant should be addressed at right time, sir.
Okay. So what I can do is like, yeah, like first of all, I can also try to go through that discussion forum, and if I can, and like, and if I am allowed to, answer those like there itself, so there like I can also try to answer them there itself. So, and yeah, I'll also try to find out who is like, basically generally what happens is there are other TAs who are
Yeah,
like
yes, sir. Yes, sir.
handling
That is the
this.
problem, sir. Yes, sir.
Yeah, so there are other TAs who handle these things. So yeah, so yeah, maybe we'll have to find out. But yeah, anyway, like if you have any questions, so you can always ask me during the live session. So
Yes, sir. Yes, sir.
yeah,
I will
and
ask. No
yeah,
problem, sir.
and yeah, so regarding the questions on discussion forum, I'll also go through them and try to answer them like, yeah, based on my knowledge. So yeah, sure. So yeah, thanks for pointing out that. So
Yes, sir. Thank you very much for nice sessions.
yeah, thanks. Yeah, bye. Thanks for joining. Good night.